Hello, welcome to this second video to support the Further Maths Conference Calculus session. In this video we're going to look at another technique that you can show your students to make connections between the calculus and other areas of maths that they've studied. In this one we're going to look at how we can connect the graphs of the circular and hyperbolic functions to some integration techniques. So here are the graphs of the circular function and the hyperbolas that students should be familiar with. Now, if I were to think about these, I can see a pattern across the equations for these three. And I can also think about what equivalent parametric forms would be. So, students should be familiar with the circle can be written as x equals a cos t, y equals a sin t. They should also be familiar with the tan and sec version of the hyperbola. I'm going to use one based on the hyperbolic functions, and hopefully by doing this students will see a pattern emerging here. So I can write a parametric form of this as x equals a cos t, y equals a sin t. Similarly, I can write a parametric form of a hyperbola this way on as x equals a sin t, y equals a cos t. Now, there is a slight issue here. This will only give us the right hand of the hyperbola if we allow t to be real valued. However, that will be sufficient for our integration, and I'm more interested in the similarities and the relationships between these and how we can see these are all variations on a similar idea, circular functions and equivalent hyperbolic functions. Okay, so now I'm going to apply that to an integration. I'm going to think about the integral of 1 over square root of x squared minus 4. Now I can relate this to an explicit Cartesian form of one of my three graphs, and it's going to be this one. That's because if I were to rewrite this is in an explicit Cartesian form, it would look like y is equal to the square root of x squared minus a squared. Technically it's plus or minus the square root, but I'm only really thinking about the right hand side, and that'll be sufficient for my integral. As a reminder, the parametric form of this was x equals a cos. Now I'm going to be doing a trig substitution, so instead of the parameter t, I'm going to use the parameter u. Similarly, y is a sin u. Okay, how has that helped? Well, the first thing we can identify is that this up here looks very much like this here with the value a is 2 in. What that suggests is that if I replace x with a cos u, this whole expression is y, which is a sin u. What does that look like if we write it out? Well, what I can say is I'm going to use the substitution x equals 2 cos u, 2 just because it's the square root of 4 here, and I had a squared. If I use that substitution, I would need dx by du, which is 2 sin u. And then my integral becomes the integral of 1 over, well, all of this thing, if I've made x 2 cos u, all of this is y that I can see down here. So if all of this is y, I can just replace that with my expression for y, which is 2 sin u. If that's not clear, you might want to rewind and just think about that bit again. Now, dx, if I multiply through by du, I get 2 sin u du. So this whole integral, because that cancels and that cancels, becomes the integral of 1 du, which is u plus c, and u here, divide by 2 and then take the inverse, I get r cos x over 2 plus c, which is what you would get if you looked at the equivalent form in the formula book. Okay, if you've got the handout now for this session, there's 2 more for you to have a go at on that. Once you've had a go at doing those, come back and see the second video where we'll talk through the solutions to them.